All right. Well, thank you, Ian, for the introduction. It's really, really nice to be here for my first, but I'm sure not my last, COLT. And I apologize that we're running late and I'm between you and lunch. I don't know what to do about it, but all right, cool. So I want to tell you about sort of a sequence of work, sort of actually applying, the ideas that you guys know, basically, the ideas of computational learning theory to the problems of reconstructing some description of a quantum state from measurement data, or coming up with some short classical string that lets you simulate a quantum state sort of well enough for practical purposes, things like that. And even if you don't care about quantum mechanics, I feel like this is a story that people in the learning theory world should know about, because if nothing else, we'll see that sort of the concepts of COLT sort of could not have been better designed for this application in some sense. So it's even though of course they were not invented with quantum mechanics in mind. So it's really nice to see how well things fit together. So you won't have to know any physics for this talk, as long as sort of when I tell you that the state of a system is this Hermitian positive definite matrix, you just believe me and you don't ask me why. I like to say that quantum mechanics is actually very, very simple once you take the physics out of it. It's just linear algebra, and that's pretty much all we'll need for this talk. Okay, so the starting point for this work is, if you like, the philosophical question, what exactly is a quantum state? Or how much information is in it? The simple mathematical answer is a quantum state is a unit vector of complex numbers, at least a pure state, meaning just like a pure superposition. We'll come to mixed states later, which are distributions over pure states. Okay, so for example, if we have a system that can be in two perfectly distinguishable states, we could label them 0 and 1, and then the laws of quantum mechanics say that we can take an arbitrary normalized complex linear combination of those states, alpha 0 plus beta 1, where alpha and beta are complex numbers called amplitudes, and that will also be a valid state for the system. Okay, so here I'm using the physicist's notation for vectors, but that's all it is. It's a notation for vectors. So, so 0 and 1 would form an orthonormal basis. Okay, they're just, these are two distinguishable states, and they span, in this case, a two-dimensional vector space. If you want to be more concrete, if this were an electron, 0 could be its lowest energy state, 1 could be its first excited state. Okay, if we were talking about a photon, they could be the states of horizontal and vertical polarization. Okay, but honestly, I don't care, right? All of these different things will lead to the same story. Okay, so now how much information is in this thing? And immediately we notice something strange, which is that the rules of quantum mechanics say that just to keep track of the pure state of a single qubit, which is something that in some sense is not in our heads. It's sort of clearly out there in the world somehow, but we need an infinite number of bits to represent it, because alpha and beta are arbitrary complex numbers, right? You could have an amplitude that encodes Chaitin's halting constant, or you know, something crazy like that in principle, right? And you know, and no one knows of any sort of decent approximation to quantum mechanics where the amplitudes would be rational numbers or would be discretized, because you know, they in any case your transformations of the states have to form a group, and you sort of very quickly generate something that's dense. Okay, so in some sense there's an infinite amount of information even in a two-level quantum system, but it is information that's not directly accessible to us. Okay, so you've probably heard that, you know, if you take a qubit and you ask it whether it's 0 or 1, well, it will tell you one or the other. It will say that it's 0 with probability absolute value of alpha squared, and that it's 1 with probability absolute value of beta squared. And once it makes a choice, it sticks with it. Okay, so it just snaps to one of the two outcomes, and then you know, we get the famous collapse of the wave function. Okay, we you know, it just sticks with whatever it said before, and so in some sense there's these infinitely many bits, and yet a measurement of the state only reveals one bit. Okay, so we might be skeptical that these infinitely many bits are sort of really there, or you know, at least we might want to investigate, you know, what do we mean by information being really there, and you know, another indication of you know, that sort of quantum states may not be quite as vast as they appeared at first actually came very early in the field. A seminal result called Halevo's theorem. Okay, and what Halevo's theorem says is, well, let's say that Alice is going to pack n classical bits into a quantum state and send them to Bob. And then Bob is going to measure the state, and he has to be able to reliably retrieve, you know, whichever bits Alice was thinking of. Okay, in that scenario, actually, in order to send Bob n bits, Alice has to send him n qubits. Okay, so not only, you know, is you know, they're not an infinite savings compared to classical information. There's no savings. You know, if Bob has to be able to read the bits out later, then, you know, you want to send n bits, you need n qubits. Okay, if Alice and Bob had pre-shared entanglement, then interestingly it goes down to n over 2. Okay, but at any rate, it's still linear in n. Okay, so, you know, even knowing that, you could say, you know, from a computer science standpoint, there is still a sort of a major problem. You could say, you know, almost like a metaphysical or epistemological problem with, you know, the whole notion of a quantum state, which is that if we have a quantum state, not just for one qubit, but let's say for n qubits, and these qubits could be entangled with each other in some arbitrary way, which is just sort of the quantum version of correlated, well then, you know, the rules say that we need to assign an amplitude to all 2 to the n possible settings of all n bits together. Okay, so that's 2 to the n amplitudes, right? For 1,000 particles, that's already more amplitudes than we could write down in the entire observable universe. Okay, so, and that's even if you only wanted to approximate the state, right? Forget about infinite precision. Okay, so quantum states are somehow these unbelievably vast objects. You know, which of course is precisely what we want to exploit in quantum computation. You know, it's sort of amazing, you could say, how long it took in the history of physics for people to really zero in on this exponentiality. because to a computer scientist, it it immediately makes you want to call into question, well, sort of, is this exponentiality really there, or are we just dealing with some kind of approximation to some better theory yet to be discovered, as often happens when we see what at first looks like an exponential blow up. Okay, but why should we worry about any of this? Well, let me give you sort of a couple of sort of more practical reasons to worry about it. My first reason has to do with a very, very central task in experimental physics, which is called quantum state tomography. And basically what this means is you've got a machine that spits out copies, of some quantum state, right? You can, run the machine as many times as you like to get as many copies as you like of this state, but you don't know what the state is, okay? And you would like to figure out, you would like to learn a classical description of your state, okay? Or in practice, it's often, prove that your state, is what you hope it is, so you can publish your paper in Nature, okay? So, but we won't assume that you know anything about the state in advance, right? It could be a completely arbitrary entangled state. And here, the difficulty is, well, if we have a state of n qubits, then the experimental effort that is needed to tomographically learn that state will, in general, clearly increase exponentially with n. Okay, why? Because that's just the number of parameters that have to be learned, right? You need 2 to the n bits even just to write down your classical description of the state. Okay, so there's clearly this exponential blow up here. The experimentalists are very well aware of that. As far as I know, the record in doing full tomography is still Rainer Blatt's group at Innsbruck was able to do tomography on an 8-particle trapped ion state. This required 656,000 different measurement settings, and for each of them you have to repeat the measurement like 100 times or something. Okay, I don't know how many grad student hours that that maps onto, but this is sort of clearly not scalable, and experimentalists have long discussed this as an issue. And if I want to sort of learn the state of my quantum computer, right, that beyond 10 qubits or so, it's fairly hopeless. Without further knowledge about what the state might be. Okay, now my second reason to sort of worry about this exponentiality is, well, I've sort of been involved in the debate for a while about, is scalable quantum computing possible at all? Okay, and there are some famous physicists and computer scientists who believe the answer is no. Some of them are up there, not merely that it will be difficult, which people in quantum computing would be the first to agree about that, but that there's some fundamental reason why it could never be done, right? And my point of view has always been, well, I hope that the skeptics are right about that, because if they are right, then that would be a revolution in physics. Right, a mere success in building a quantum computer seems almost boring by comparison. Okay, but it would be nice to know. For me, this was one of the main reasons to try to build it. I like to say that for me, the #1 application of a scalable quantum computer is simply to disprove the people who say it's impossible. Okay, it breaks some crypto, it simulates some quantum systems, but that's not really why I'm in this. Okay, so. Of course, ultimately, we hope to, have an actual device that will settle this debate. Okay. In the meantime, one response that one could make is, well, if if nature works a certain way, then tough cookies, right? We don't get to sort of declare a priori that, certain kinds of exponentiality are just, forbidden, right? Ultimately, it's a question of physics. Okay, but there's also, the extended church Turing thesis has a certain appeal to me also. And, I think there's another sort of line of attack one could make, which is, the skeptics find it implausible that, that you could have any physical device that would sort of manipulate an exponential amount of information in some sense using only polynomial resources. Okay, but we can interrogate, well, is it really an exponential amount of information? In what sense is a quantum state of n qubits actually like 2 to the n information? And, in what sense is it more like just sort of polynomial in n information, but that we can somehow access in a very weird way? Okay, so the sort of the theme of this talk is, can we tame the exponential beast using the weapon of COLT? Okay, and so can we sort of take these exponential quantum states and somehow shrink them down to a reasonable size by viewing them through an operational lens of what information could we actually extract from the state by making, let's say, reasonably simple measurements, and and what would be needed to summarize that information. A very simple analogy, but an illuminating one, I think, is, well, if we considered probability distributions over n-bit strings, then, just like quantum states of n qubits, these also require an exponential amount of information to specify them, even approximately. Okay, and yet, if someone hands you a sample from this distribution over n-bit strings, it's pretty clear that you're only getting n bits. Sometimes you're not getting 2 to the n bits, right? And so, we'd like to say that quantum states are somehow more like probability distributions over n-bit strings than they are like 2 to the n-bit strings. Okay, of course, they're not exactly probability distributions because they involve complex numbers, which are different, and they're, not just non-negative real numbers. Okay, but, in many sort of learning theoretic respects, they sort of act a lot like they were probability distributions, and you'll see a bunch of examples of that. Okay, so I want to survey about 14 years of results showing how standard tools from COLT can be used to upper bound the effective size or effective dimension of quantum states. Here's just some of the papers I'll be talking about. And the lesson that we'll be seeing is sort of the linearity of quantum mechanics, the fact that we're just dealing with linear algebra, and that we're so restricted in how we can actually access these states via measurement, sort of helps to tame the exponentiality and sort of hide it from our view for many purposes. Okay, so let me start my narrative, I guess, with a little variant of the problem we considered before with Halevo's theorem. Okay, this is formally it's called random access coding. Okay, but I like to call it the absent-minded advisor problem. Okay, so the scenario here is that we have a thesis advisor. Okay, and like most advisors, this one is infinitely wise and infinitely benevolent, okay? But he's also very busy, and he doesn't really, he can't really remember what each of his students are working on, okay? So his goal is to just dole out the same generic advice to all the students, which those students should be able to apply to whatever their problem might be. Okay, so this will be a quantum advisor. We will let the advice be a quantum state. Okay, and now the question that we're going to ask is, can you give all of your grad students the same state of, let's say, a reasonable number of qubits, polynomial in n, such that each of the students can just measure this state in order to learn the answer to any one n-bit question of their choice? Okay, so there's 2 to the, so this state will encode 2 to the n different bits of information, but each student need only be able to extract one of the bits, and then the state can collapse. Okay, is this possible? Okay, and you can start thinking about, well, how would I do it? I could encode 2 to the n bits in the 2 to the n amplitudes, but the trouble is that if you make a measurement of this state, the probability is astronomically small that you'll see something that depends on the particular amplitude you were interested in. Right? You'll probably just see something random that you don't care about, the answer to someone else's thesis problem. Okay, so in fact, there's a beautiful result by Ashwin Nayak as well as Ambayanis et al. From 1999, which says that the answer to this question is again no. Okay, even if each student only needs to be able to extract 1 bit of information, still, if we needed to provide random access to, say, 2 to the n different bits in the state, then the state would in general have to have about 2 to the n qubits. Okay, so you don't even get in any asymptotic savings over classical encoding. Okay, so that sounds like kind of a downer. Now let me turn that lemon into some lemonade for you. Okay, let's view that more positively. Okay, well, what it's really saying is that in some sense, suppose that Alice has some n-qubit quantum state, which I'll call psi, and she wants to describe it to Bob. Maybe not perfectly, okay, but just well enough that, well, Alice sort of knows that Bob has some collection of yes or no measurements that he might be interested in making. Alice doesn't know exactly which measurement Bob would want to apply, but she knows that it belongs to some set, which I'll call S. Okay, and so now we can ask the question, how many classical bits would Alice have to send to Bob to allow Bob to calculate the outcomes of any of those measurements in the set S? Okay, to sort of let Bob simulate having the quantum state. And we'll ask in terms of both n, the number of qubits of psi, as well as the size of this set S of measurements. Okay. Okay, so, the obvious bounds is, well, if Alice sends Bob exponential in n classical bits, then she could just send a complete classical description of psi, and she's done. Also, if she could send order S bits, then she just sends the outcomes of all of the measurements, like the probability that each of the Bob's measurements returns yes, and then Bob is again happy. Okay, the more surprising thing is that actually it suffices for Bob to send, it suffices for Alice to send Bob, a number of bits, which is polynomial in n and logarithmic in S. Okay, so even if there were exponentially many different measurements that Bob might want to apply, Alice only has to send polynomial in n classical bits. Okay. What? Yeah, that's right. That's right. So, and if you think about it, this is, well, actually, we'll see why this is true, right? But, and we'll give an actual procedure for Alice to compute this compressed representation and for Bob to extract the measurement results from it. Okay, but sort of abstractly, this is almost just like a converse of the negative result that was on the last slide. Okay, so the picture is when we think of the behavior of an n-qubit state with respect to all possible yes-no measurements, it is this astronomical, super astronomical object. Okay, but if we, for example, said I only care about the outcomes of all possible yes-no measurements that could be implemented using a circuit of size at most n squared, a reasonable size circuit, well, then, there's at most exponential in n number of such measurements, and now the quantum state shrinks down to a much more manageable size. Now I can actually describe all of this with a polynomial-sized classical string. Okay, so an interlude before I explain that is the concept of a mixed state. Okay, a mixed state in quantum mechanics is just a sort of a representation of a probability distribution over different superposition states. Okay, so you have, quantum uncertainty, but then ordinary probabilistic uncertainty on top of it. And the mixed state sort of summarizes all of the information that is actually measurable in such a situation. Okay, and if the way we represent it is if I have like a bunch of quantum states where each state psi sub I appears with probability p sub I, then I form a Hermitian positive semi-definite matrix by just taking a convex combination of these outer products of psi I with itself, right? Just projections onto psi I, and so I form this matrix which I call rho. Okay. So from this point of view, a general quantum state in d dimensions is a d by d Hermitian positive semi-definite matrix with a trace of 1. Okay, if it's a diagonal matrix, then that's the special case where we're talking about a classical probability distribution. If it's a rank 1 matrix, that's the special case where the quantum state is pure. Okay. And the one big subtlety here is that the same mixed state could be written in different ways as probability distributions over pure states. Okay, so for example, if I have 0 with probability half and 1 with probability half, that is physically identical to having 0 plus 1 with probability half and 0 minus 1 with probability half. Right? They give rise to exactly the same matrix. Okay, so in this formalism, we can easily represent what a 2-outcome measurement will do. Okay, any 2-outcome measurement just corresponds to some, again, a d by d Hermitian positive semi-definite matrix, which I'll call E. Except now the trace doesn't have to be 1. We just require that all of the eigenvalues lie between 0 and 1. Okay, and then if I apply that measurement to the mixed state rho, then it accepts with probability equal to trace of E times rho, and it rejects with probability 1 minus trace E rho. Okay, you can derive that rule from sort of the usual, squared absolute value probability rule that I mentioned before. So I'm not sort of introducing a new law of physics here. This is just formalism. Okay, so now how does this theorem work about sort of compressed representations of quantum states? Okay, well, the picture is, we've got Alice and Bob. Okay, Alice has this n-qubit state, rho, in mind that she's trying to describe to Bob somehow. I'm just assuming for simplicity that rho is a pure state. It would also work with rho being a mixed state. Okay, so now here's the idea. In the beginning, Bob knows nothing whatsoever about Alice's state. So he's just going to guess what it is, and he's going to make the dumbest guess possible, which is he's going to guess that it's just what we call the maximally mixed state. Okay, which means just the state whose matrix is the identity matrix, divided by the dimension. Okay, just like, which corresponds to, just a uniform distribution, if you like. It's the fancy way of saying a uniform distribution. Okay, and now it's possible that, that maybe with respect to the measurements in the set S, maybe rho does just act like the maximally mixed state. If so, great, then we're done. We've got nothing further to do. Okay, more likely, there's some measurement in S on which, this hypothesis is going to lead Bob to a badly wrong guess. Okay, so, there will be some measurement E sub t on which such that trace of E sub t rho will be very far from trace of E sub t times, rho 0. Okay, so if so, well then, Alice can tell Bob what that measurement is and what the right answer should be, and Bob can use that to improve his hypothesis. Okay, so we repeatedly let rho sub t be this hypothesis obtained by starting from rho sub t minus 1, then performing the measurement E sub t, and post-selecting on getting the right outcome. Okay, post-selecting just means, I just make the measurement and I consider what the state would be, assuming that I get the right answer for the tth measurement. Okay, so it's very boosting-like what we're doing here. Okay, so Bob's hypothesis keeps improving. Now one sort of question that has to be answered here is, why is it legitimate to assume that Bob can just keep reusing the same quantum state over and over for all of the iterations of this learning procedure? Okay, because after all, as I told you, measurement in quantum mechanics is a destructive process, right? You measure, your state, may be dead. Okay, but there's an extremely useful fact in quantum information. It gets used all over, okay? And what it says is, well, look, if I took a state like 0 plus 1, over square root of 2, and I measured it in the 0 and 1 basis, then that's going to be a very destructive measurement, right? I'll see 0 or 1 with equal probabilities, and whichever one I see, my new state is just totally different from my old state, okay? But on the other hand, if I took a state that was already very close to 0 or to 1, and I measured that in the 0-1 basis, well, then that's not going to damage my state by very much. Okay, because most likely my state will just snap to whichever basis vector it was closest to, right? So if there's sort of not much randomness, then there's not much disturbance either. Okay, this was discovered independently a bunch of times. Most people call it the gentle measurement lemma. I call it the almost as good as new lemma. Okay, but the formal statement is, suppose that a measurement of a mixed state rho yields one particular outcome with probability very close to 1 minus epsilon. Then after the measurement, it is possible to recover a state rho prime, which is very close to rho. Okay, in the usual distance metric between quantum states, which is called the trace distance, its distance from rho is at most square root of epsilon. So actually, as long as we make sure that our measurements yield nearly determinate outcomes, we can keep reusing the same state over and over and making many measurements on it. Okay, super duper useful fact. So now, if you remember this iterative learning procedure, right, by definition, like if and when the procedure ever terminates, Bob must have a hypothesis state that, it may not be close to the true state rho in trace distance, but it will effectively simulate rho for all the measurements in the set S. Right? If it doesn't, then we wouldn't have terminated. Okay? So the only remaining question is, well, how many iterations do you have to do until this thing terminates? Okay? And my claim is that actually the number of iterations that you need is only polynomial in the number of qubits, not exponential. Okay? Why? Well, let's just let P sub t be the probability that sort of the first t post-selection steps all succeed, right? Then we're going to bound P sub t from two directions, okay? So I should say, I'm assuming here that we do a little bit of amplification of our state, right? So instead of just having one copy of psi, we'll imagine that Alice starts with log of n copies of psi, right? This is what I do to make my measurement outcome sort of nearly determinate, by, a Chernoff bound, right? And, and this does not increase the complexity of the procedure by very much, only by a log factor. Okay, so, and now what you can say is that, well, if Bob had happened to start with the true state rho rather than the maximally mixed state, well, then he would have been cooking, right? Then every post-selection step would have succeeded with probability close to 1, okay? And from that it follows that if I start with the maximally mixed state, well, I can decompose the maximally mixed state in any orthonormal basis I like. That's just a linear algebra fact, right? In particular, I could decompose it in an orthonormal basis in which one of the vectors is the state that is the sort of the true state. Okay, and so that means, well, I can view it as, well, with probability 1 over exponential in n, I picked the right thing. And so the entire process has to succeed with probability at least 1 over exponential in n. okay, n log n, that being the amplified number of qubits. Okay, but then on the other hand, the whole point of this procedure was that I only pick a new measurement if, even conditioned on success at all the previous measurements, I have a good chance of getting the wrong answer on this new measurement. Okay, and that means that after t steps, the probability that my t post-selections could have all succeeded goes down exponentially with t. Say it's at most 2/3 to the t. Okay, but now if we just combine these two facts, well, then we see that, that the procedure has to stop after t is at most n log n. Okay, so it suffices for Alice to tell Bob about n log n measurements using only about log of s bits to specify each measurement. Okay, so now the reason why I did all this, what came from the complexity zoo, I guess, and wanting to understand this complexity class called BQP/QPoly, which is actually my email address. Also, I just like this class. Okay, BQP is bounded error quantum polynomial time. It's what you can do efficiently with a quantum computer. So, it's the quantum generalization of P, if you like. /QPoly means I get this super powerful quantum advice state, right? Which can be chosen by an all-knowing advisor, but it only depends on the input size n. And it has polynomial in n qubits. So it's just a quantum version of Karp-Lipton advice. Okay, and so now it remains a central open problem in quantum complexity theory to this day. Is BQP/QPoly equal to BQP/Poly? Like, does being given quantum advice ever give you more power than being given classical advice? Beautiful question. Okay, what I was able to show is that, well, at least, BQP/QPoly does not contain every language. Which, a priori, it sort of could have, right? It's, it's not obvious. In fact, Harry Berman here in Amsterdam, when challenged me, can I rule out that BQP/QPoly contains every language whatsoever? Right, So, okay, so what I could show is that whatever you could do with quantum advice, you can also do with polynomial-sized classical advice, provided that your quantum computer has this additional power of post-selection. And this follows almost immediately from the learning procedure that I showed you before. Okay, and if you're wondering, this BQP with post-selection, I have another theorem that says that this is precisely equal to the classical complexity class called PP, if you know or care what that is. Okay, so now I want to sort of get closer to sort of learning theory with a different variation on the kind of theorem that I showed you before, which I called the quantum Occam's razor theorem. Okay, that is William of Ockham. That I think is a Gillette. So, okay, so now here's the setting here. Let's say that I've got an unknown entangled state of n particles. I'll call it psi. And now, let's suppose, not that we have a finite list of measurements as before, but just, now let's imagine that we've got a probability distribution over two outcome measurements. Or I'll call the distribution mu. Okay, it could even be a continuous measure. Okay, and let's say your goal is you would just like to learn how to simulate psi with respect to most measurements drawn from mu. Okay, so you'd like, for sort of a 1 minus delta fraction of measurements from mu, you would like to, be able to predict the probability that that measurement will accept psi to, within an additive error of epsilon or something. Okay, let's say that that's your goal. Okay, so then what my learning theorem says is that, it suffices to do the following. Okay, some sample complexity m, which is L of n. So you just draw m measurements independently from mu. Then you go into your lab and you estimate the acceptance probabilities of each of those measurements on your target state psi. Then you just find any hypothesis state that is approximately consistent with all of those measurement outcomes, and then with high probability, that hypothesis state will generalize. Okay, and the interesting part here, at least to people in the quantum state tomography world, the sort of shocking thing to them was that the sample complexity only increases linearly with the number of qubits. Okay, so you get an exponential improvement over the amount of sample data that would have been needed to do full quantum state tomography. Okay, and how is this done? Well, to prove this, as I said, I can just take concepts that this community already invented and pretty much use them off the shelf. Okay, so in particular, I use this notion called fat shattering dimension, which I sort of I invented for myself before discovering that you guys had very conveniently invented the exact same thing. I wouldn't have called it that, but. Okay, and so just, I'm sure some of you have seen it. For those who haven't, this is a definition. It's sort of like a generalization of VC dimension to deal with real-valued concept classes, where I say, if I have like a set, I say it's gamma shattered by my concept class. If sort of for all 2 to the n possible behaviors that look like this, I can find some function in my hypothesis class that's consistent with that behavior, right? If that's true, then I say that the thing is gamma shattered. Okay, and then the gamma fat shattering dimension is just the size of the largest set that's gamma shattered by my concept class. Okay, and there are known results in learning theory that say anytime you've got a class of real valued functions with bounded fat shattering dimension, then it can be learned with a number of samples that scales only linearly with the fat shattering dimension. Okay, so we can use all of these results. So then the one remaining thing to do is we need to upper bound the fat shattering dimension of quantum states considered as a hypothesis class. Okay, but here it turns out that this sort of lower bound for this absent-minded advisor problem that I mentioned earlier in the talk, which is something that quantum computing people did for totally independent reasons. If you just look at it from the right angle, it is an upper bound on fat shattering dimension, right? Sort of that is what they were doing. They just didn't call it that. Okay, so in particular, you can get that sort of, if I define a set of functions that map an n-qubit measurement E to trace of E rho, then the gamma fat shattering dimension of that class is like the number of qubits divided by gamma squared. And that's actually tight. Okay, so thanks, Ashwin. Okay. So, okay, you may wonder, how do we actually find the hypothesis state? Well, one, very simple thing that we can commend to the experimentalists is just solve this convex programming problem, right? So, sort of you've got your empirical measurement outcomes, call them B1 up to Bm, and then just find a hypothesis state, sigma, that sort of minimizes this functional. Right? That will generalize. Okay, and what's nice is, this is something that, because it's convex programming, can at least be done in time polynomial in D. I mean, yeah, it's exponential in the number of qubits. You're not going to avoid that. But at least it's not doubly exponential, the number of qubits. Okay? But it gets better, because when I told Elad Hazan about this a decade ago, he was able to design a special learning procedure, a special procedure for this convex programming problem, which actually exploits its structure to run in nearly linear time. Okay, and I just learned this morning that this result of Hazan has actually been used for all sorts of things since then in classical learning theory. Okay, but it came from my question about quantum state learning. Okay, so with an undergraduate, Eyal Dechter, we actually implemented Hazan's algorithm, and we simulated it on, simulated quantum state data. We looked at how the number of sample measurements scales with the number of qubits. Of course, we could only simulate up to about 10 qubits. Okay, but long story short, the result of these experiments is that my theorem appears to be true. I can even show you a graph. You see, the sample complexity, it looks linear, right? But okay, I guess the more interesting part is not only is it linear, but the constants are totally fine. Okay, so that's what the experimentalists like. And just very, very recently, a team in Rome has actually implemented for the first time my quantum state pack learning on real experimental data, and that's a paper that is still in preparation. Okay, so in 2010, Andy Drucker and I had a result that sort of tries to get the best of both worlds of the post-selection and quantum learning results. So what it says is, suppose that you're given an n-qubit state rho and also some upper bound on complexity t. Then there is some polynomial time measurement, v, which I could make on a reasonable number of qubits, like polynomial in n and t, such that if that measurement passes, so like it says, like my verification test says yes, then I know that I must have a state which is not necessarily rho itself, but which can be used to efficiently simulate rho on every yes or no measurement that can be implemented using at most t quantum gates. Okay, so like there's a verification test. If it passes, my state is sort of as good as rho with respect to all bounded complexity measurements. And in complexity terms, this actually implies a stronger upper bound. BQP with quantum advice is actually contained in quantum MA, quantum Merlin-Arthur with classical advice. Okay, or say it another way, trusted quantum advice can actually always be decomposed into trusted classical advice combined with untrusted quantum advice. Okay, the proof, again, uses sort of boosting-like techniques together with results that sort of say if I have a class with bounded fat shattering dimension, then it has sort of a bounded size epsilon cover. So it's completely, again, sort of, a lot of off-the-shelf tools from learning theory and combining those with quantum information theory tools. Okay, so now I want to tell you about a brand new result, which is not yet written up. But the new result, well, I couldn't think of a good name for it. Just a week ago, Steve Flamia suggested that I call this shadow tomography, which, I don't know, sounds kind of cool. So all right, so let me tell you my new theorem, okay? This solves an open problem that arose from the study of quantum money, in which I had been asking for several years. I don't know if anyone else cared about it, but I did. So it says, let rho be an unknown quantum mixed state, say in d dimensions. And now suppose I have a bunch of known yes or no measurements, E1 up to EM. Okay, and what I want is to estimate the probability that every single one, for each EI, I want to know approximately trace of EI rho. So I want to know, for each measurement, what is approximately the probability that it accepts rho, so within additive error epsilon. Right? And once again, it's pretty obvious that I could, do that if I have m copies of rho, right? I just measure each one separately. It's also obvious that I could do it if I had about d squared copies of rho, because then I can just do full quantum state tomography, and then I'm done. Okay? Here's the interesting result, that it is actually possible to do this, to learn all of this data by starting with a number of copies of rho, which is polylogarithmic in both m and d. Okay? So I can learn the outcomes of exponentially many different measurements, on an n-qubit state using only a polynomial number of copies of the state. Okay? By the way, I don't know whether there has to be any dependence on d here. Maybe this can be eliminated. I know that there has to be at least a log m over epsilon squared dependence. Okay, so now what the central difficulty in proving this theorem is, well, again, the destructive nature of measurement, right? If I start with only a few copies of rho, well, then I can start trying to learn the values of trace EI rho, but that's going to destroy my copies. So how do I sort of preserve my copies to be reused another day, right? I can try doing amplification like before, but in this case, I could have some trace EI rhos that are just on the knife edge between acceptance and rejection. right? Nothing says that all these, probabilities have to be close to 0 or close to 1. Okay, so what do I do then? So the main idea of the proof is to use, a result that I sort of wrongly claimed in 2006. There was an error in my proof. It was just recently fixed by Harrow, Montanaro, and Lin. So here is the statement of I guess my result for some definition of I'll say their result, okay? So, it says, if I have an unknown d-dimensional state, a bunch of 2 outcome measurements, I can at least solve the decision problem. Is there sort of a measurement in this list that causes rho to, that accepts rho with a high probability? That I can do using only about log of m copies of rho. Right, and sort of the idea is I can make a bunch of measurements, on these copies of rho, and yes, I might destroy the copies, but if I destroy the copies, I can sort of detect that I destroyed them using some control qubit, and the destruction can only happen if I'm in the case where there is a measurement that I accept with high probability, so then I know the answer. Okay, now by combining this with just some binary search, it's possible even to give a procedure that if there is a measurement in my list that accepts rho with a high probability, then it finds that measurement. Okay, and that I use some polylog in m number of copies of rho. Okay, and so now all I do is I use my post-selected learning algorithm from, that I showed you before. But now each time I need to know a new measurement, EI, on which I'm going to fail with high probability, even conditioned on succeeding on all the previous ones. Okay, now I no longer have an infinitely benevolent advisor to tell me what that measurement is. But I can find it myself by using this measurement procedure here. Okay, so then I put everything together. I get some polylog D from this and some polylog M from here. And that's my shadow tomography procedure. Okay, does something that, I think a lot of people's guess was that, and my initial guess also was that this would not be possible. But, yeah, so, okay, another new result that we've been working on is, so Elad Hazan challenged me a couple years ago. All right, that's nice that you have this pack learning theorem for quantum states, but pack learning is kind of passé, he tells me. And, really what we care about these days is this online adversarial learning. So can you do that for learning quantum states? So, yeah, we can do that. We can do that. So, we can, in fact, my post-selected learning procedure, if you think about it the right way, it almost immediately gives you that. Alternatively, you can also use general convex optimization tools, upper bound the sequential fat shattering dimension of quantum states, and that gives you like some regret learning result for quantum states, which will now work even in the agnostic case, even if there's no actual quantum state that all of your data came from. So that's kind of cool. Okay, and that's we're still writing that up. So to summarize, the tools of COLT have sort of let us show that in many scenarios, the exponentiality of quantum states is more bark than bite. In other words, there's a short classical string that specifies how your quantum state behaves on any 2-outcome measurement that you could actually perform. Applications of this range from complexity theory to, experimental quantum state tomography, and I hope that we'll find more applications. Unfortunately, these results do not seem to generalize to measurements with a huge number of outcomes or to learning of unknown quantum processes. Okay, and there it's easy to give counterexamples where, you really would need an exponential number of trials if I wanted to learn, say, the behavior of this unknown process on exponentially many different input strings. Okay, so it's very special to sort of the linear algebraic structure of 2-outcome measurements on unknown, or at least few outcome measurements, I should say, on unknown quantum states. Okay, as I see it, probably the biggest future challenge is to find subclasses of states and measurements for which these learning procedures are efficient, not only in sample complexity, but also computationally. And I should mention some very recent work by Andrea Rochetto, which shows that for a very important class called stabilizer states, plays a central role in quantum error correction. Actually, my pack learning theorem can be made computationally efficient there. I would love to know other classes of quantum states for which that's true. So let me stop there. Thank you. Yeah.
I am wondering why you're not using the matrix exponentially gradient algorithm for this demography problem. Because it was exactly designed for that.
Yeah, so I should have mentioned in the talk. Okay, all right. The question was, why do I not use matrix exponentials? So in fact, when I gave a talk about that result at Caltech, Fernando Brandao pointed out to me afterward that sort of the top level of the learning procedure, which is the part where I use this post-selected learning, it can indeed be replaced by something with matrix exponentials and like a Jaynes maximum likelihood estimator, right? You get exactly the same sample complexity as if, like this way is more intuitive to me. You can do it that way. You get the same sample complexity, and then in any case, you still need that sort of earlier result. This you still need this part, but you can then just take this part that searches for the measurements to condition on, and you can plug that into some matrix exponential based algorithm. A good point. No.
It makes sense to consider this in an adaptive data analysis setting.
Okay.
Instead of these m measurements being given up front, the next measurement is the function of the output of the previous.
Yep. That's exact. Unless I'm so the question was about adaptivity. Unless I'm misunderstanding, that's basically exactly the online learning scenario, right? Which these new results that we have precisely address that.
So the next one in the sequence can be a function of.
Oh yeah, absolutely. I mean, chosen by your worst enemy who's seen everything you've done so far, right? And still, you're gonna, you're gonna output hypotheses as you go, and some of them could be wrong, but no more than this number, which is polylogarithmic in the dimension of the Hilbert space. So it's there's not even a factor here that's like square root of the number of measurements that you've seen. That you do get in the agnostic case, but in the non-agnostic case, it's you make very few mistakes. Yeah.
So you didn't mention anything about computational complexity.
Yeah.
You don't have to play too much with the
Yep. Yeah. Yeah, so as I said, computational complexity, just like analogous to the case of classical learning theory, like that's kind of, a wide open sort of subject for investigation, right? Now, it's apparent that, we cannot hope for a general learning procedure that will take time polynomial in the number of qubits, because we don't even have that in the classical case. Right? There's, all these concept classes that are cryptographically hard to learn. Right? So surely, the quantum case contains the classical one as a special case. So surely we will also have exponential and n complexity here in the, in the worst case. What's more interesting is that by using convex programming over all the, d by d positive semi-definite matrices, we can observe that the complexity is not, even in the quantum case, is no worse than exponential in n, right? So it's, it's merely, polynomial in the dimension of your quantum state space. In general, you can't hope for anything better than that, right? For cryptographic reasons, but still, I hope that there, just like there was in classical learning theory, that there might be many other interesting special cases where the learning could be done computationally efficiently.